Hello everyone. Today I am Krushi. Today we will read about the chapter Ionic solids. Ionic solids contain an ionic bond which is formed between atoms by the complete transference of one or more valence electrons of one atom to the other atom. Therefore, in this type of bonding, one atom completes its octet and acquires noble gas configuration by acquires a positive charge and the other which gains the electrons acquire a negative charge. These two oppositely charged species come closer due to electrostatic forces of attraction and form an ionic bond. Since electrostatic attraction leads to decrease of potential energy and therefore the potential energy of the system becomes less than it was before the formation of the ionic compound. The electrostatic force of attraction which holds the oppositely charged ions together is known as ionic bond or electrovalent bond. The compounds containing ionic or electrovalent bonds are called ionic compounds. Now, the formation of ionic bond. An ionic bond is formed when one or more electrons are completely transferred from one atom to another atom so that both the atoms acquire stable noble gas configurations. Let us illustrate the formation of ionic bond by considering the example of sodium chloride. Sodium atom has only one electron in the valence shell and by losing their electron it can acquire stable electronic configuration neon. On the other hand, chlorine atom has 7 electrons in its valence shell and needs only one electron to complete its octet. Thus, both the atoms can complete octet if sodium atom gives one electron to chlorine atom. This tendency is responsible for bonding between sodium and chloride atoms. Therefore, sodium gives electron and becomes positively charged. Na positive ion, while chlorine takes up the electron and becomes negatively charged. Chlorine ion. These two ions are then held together by electrostatic forces of attraction which constitute an ionic bond. The formation of ionic bond between sodium and chlorine may illustrate by the following electron dot pictures. The formation of ionic bond between sodium and chlorine may be illustrated by following electron dot. When atoms combine by electron transfer, the number of electrons gained or lost must be equal so that the resulting compound on the whole is electrically neutral. The number of electrons gained or lost by an atom in the formation of ionic bond is equal to its electrovalency. Atoms that radially Atoms that radially lose electrons are said to be electropositive, while those which radially gain electrons are called electronegative. Let us consider the another example of calcium chloride. Calcium has two valence electrons and can acquire the configuration of argon while losing these two electrons in the formation of CaCl2. The two valence electrons of calcium are transferred to two chlorine atoms, and all the ions thus formed have noble gas configurations. Similarly, in the case of magnesium oxide, magnesium has two electrons in the outermost shell and oxygen has 6 electrons in the outermost shell in the formation of magnesium oxide. Both magnesium and oxygen attain the noble gas configurations by transfer of two electrons from magnesium to oxygen. The electrostatic force of attraction between Mg2 positive and O2 negative results in the formation of an ionic compound Mg2 positive plus O2 negative gamete. In this compound, the electrovalency of magnesium and oxygen is plus 2 and minus 2 respectively. Now the general characteristics of ionic solids. The ionic solids have the following characteristic properties. First, crystalline nature. In general, ionic compounds are crystalline in nature. X-ray studies of these compounds have shown that they do not exist in the molecular form but consist of ions of opposite charges arranged in some definite geometric pattern. Each ion in the crystal is surrounded by a definite number of oppositely charged ions. The geometric arrangement of ions is different for different ionic substances. The mode of arrangement depends upon the size of the ions and also on the respective charges on them. For example, in sodium chloride crystal, each sodium ion is surrounded by 6 chlorine ions. This arrangement is extended throughout the crystalline lattice. Second, high melting and boiling points. In general, ionic compounds have high melting and boiling points and high heat of fusion and vaporization. It is because of the strong electrostatic forces of attraction between the oppositely charged ions. Consequently, a large amount of energy is required to overcome interionic attraction, which results in the increased melting and boiling points. The variation in melting points in different ionic compounds are mainly due to first the charges on the ions, second ionic radii. The closer the ion in crystal, the larger will be the electrostatic forces of attraction and consequently higher will be the melting point. For example, in the case of sodium halides, the melting points decrease from NaF to NaI as the size of the anions increase from F negative to Cl negative. The forces between the Na positive and halide ion become weak and consequently melting point decrease. In case the interionic distance is almost the same between two compounds, the melting point is determined by the charges of the ion. For example, NaCl and BeO have almost similar internuclear distances. The melting point of NaCl is 1073 Kelvin while the melting point of BeO is 2195 Kelvin. The higher melting point of BeO is due to stronger interionic attraction between doubly charged Be2 positive and O2 negative ions in comparison to attraction between singly charged Na positive and Cl negative ions. Third, hardness. Ionic compounds are hard and rigid. The hardness of the compound is due to the strong electrostatic forces of attraction between oppositely charged ions. Hardness of these compounds increases with the decrease in interionic distances and increase in ionic charges for crystal with similar structures. For example, LiCl and SRO have similar structures and their interionic distances are also the same. SRO is harder than LiCl because of higher charge of ions in SRO than in LiCl. Similarly, NaCl and CaS have similar structures and nearly the same interionic distances. But CaS is harder than NaCl because of high charge on ions. On the other hand, all the alkaline earth metal oxide MgO, CaO, SrO, and BaO have similar structure and their ions are also doubly charged, but their interionic distance increases in the group from MgO to BaO due to increase in their interionic distance, their hardness decrease. Fourth, brittleness. Ionic compounds are usually brittle, that is, they can be easily broken into pieces on applying stress. An ionic crystal consists of closely packed ions of opposite charges. When enough force is applied to ionic crystal, one layer of ion moves across the next layer As a result, the ions of like charges come near to each other. This causes instability because of repulsion between similar ions and result into breakdown of the crystal. Next, solubility of ionic compounds. Ionic solids are generally soluble in water and other polar solvents having dielectric constants. Since water has a high dielectric constant, it decreases the electrostatic forces of attraction between the ions. As a result, the ions get separated from one another to give a solution. Thus, ions in solution acquires greater freedom of motion. Another favorable factor is that water acts as a dipole, having negative and positive ends. When an ionic compound is dissolved in water, the positive end of the dipole interacts with the negative ion, while the negative end of the dipole interacts with the positive ion. Due to this strong interaction between the ions and the solvent, large amount of energy is released. This is known as hydration energy. The hydration energy released is greater than the crystal energy, which hold the ions. Consequently, the crystal lattice breaks and goes into the solution. Most of the organic solvents have low dielectric constant and are not highly polar. Hence, ionic solids are only slightly soluble in organic solvents. Conduction of electricity. The ionic solids consist of ions. They do not conduct electricity in solid state. The reason is that the anions and cations on account of electrostatic forces are held strongly at particular positions in crystal lattice and are not free to move. Hence no current flows. However, as the temperature is raised, there is increase in kinetic energy of the ions when the substances are heated to high temperature so that they melt. The kinetic energy of ions increases to such a large extent that they overcome the attractive forces and become mobile and are thus able to conduct electricity in the molten state. Similarly, when the ionic compounds are dissolved in water or some other solvent, the ions become free and therefore they conduct electricity in dissolved state also. Seventh, ionic reactions. Ionic compounds split up into oppositely charged ions when dissolved in water. The chemical reactions of ionic compounds are characteristics of the constituent ions and are known as ionic reactions. Such reactions occur almost instantaneously. Now, eighth, non-directional character. The ionic bond is non-directional. In ionic compounds, each ion is surrounded by oppositely charged ions held together by electrostatic forces. These forces are uniformly distributed all around the ion. That is, electric field is non-directional. Therefore, the ionic bond is non-directional. Structures. We have learned that in the formation of crystal, the constituent particles get closely packed together. The closely packed arrangement is that in which maximum available space is occupied. The closer the packing, the greater is the stability of the crystal. All crystalline substances have definite orderly arrangement of their constituent particles in three dimensions. The regular arrangement of constituent particles of a crystalline solid in three-dimensional space is called space lattice. If we carefully look at space lattice, it is observed that we can select a smallest repeating pattern, which is repeated over and over again in the whole crystal. This smallest repeating unit in space lattice, which when repeated over and over produce the complete lattice, is called unit cell. This smallest repeating pattern or unit cell represents the shape of entire crystal. It must be remembered that while drawing the structure of ionic solids, we do not draw the complete crystal lattice but a unit cell. In the simple ionic compound, generally two types of arrangements are possible. These are cubic closed packed arrangements and hexagonal closed packed HCP arrangement. The larger ion, that is, anions, adopt these arrangements. The CCP arrangement, also known as FCC arrangement, can be obtained by placing atoms at all the corners of the cube and at the center of each face. There are six faces. This arrangement is also called ABCA arrangement. There are four atoms per unit cell in this arrangement. The HCP arrangement is drawn by placing atoms at all corners of the hexagonal faces and at their centers. One layer is made in between these two identical layers. If we join opposite corners of a face, we get six triangles. The second layer is formed by placing the atoms above alternative triangles. This arrangement is also called ABA arrangement. The cations occupy the interstitial sites of these arrangements. As already learned, there are two types of sites which are commonly occupied. These are octahedral sites and tetrahedral sites. There are two tetrahedral sites for each atom and one octahedral site for each atom. Location of interstitial site in closed packed arrangements. First is CCP arrangement. The octahedral sites in CCP arrangement are between the two anions. Obviously, these are at the center of every edge and in the body center. Only the octahedral sites of top face by dark spheres, the hollow spheres represent anions. If we carefully see the CCP arrangement, we observe that it has 8 small cubes. Each cube has 4 anions at the alternate corners. The center of small cube becomes the tetrahedral site. There are 8 small cubes and therefore there are 8 tetrahedral sites. Only tetrahedral site is shown filled. Now next is HCP arrangement. In HCP arrangement, the octahedral and tetrahedral sites are shown. We have learned earlier that the second layer in HCP arrangement is made by placing atoms on the alternative triangles in the face. For example, B layer is formed by placing atoms above the triangle marked crosses. The octahedral sides correspond to other triangles. The tetrahedral sides are shown above and below each atom. For simplicity, only the tetrahedral sides above the bottom layer are shown filled. Let us discuss some important structure of two types AB and AB2. In the structure of AB type, the two type of ions have same coordination number, that is number of nearest neighbors. However, in compounds of AB2 or A to B types of two kind of ions which have different coordination numbers, which are in the ratio of 2:1 or 1:2 respectively. It may be noted that we consider close packed arrangement of ions, though the closed packed arrangement may slightly expand in order to accommodate the opposite ions. As a result, the structure may be slightly open up structure.